We're continuing our work on binomial probability distributions, and we're going to look at how to determine the mean, the variance, and the standard deviation. And despite what that says, actually this stuff's not too bad. So if you know already about Bernoulli trials, binomial probability distributions, or binomial random distributions, random variables, this is really not that hard. So that's not, it's not going to blow your brains out. So a learning goal for this is we're going to use parameters to calculate the mean, which is given by NP, the variance, which is given by NPQ. Now that NPQ can be written as NP times 1 minus P, because Q and 1 minus P, if Q's a fail, it's in a binomial situation, it's the complement of P, probability of a success on an individual Bernoulli trial. So we know also from our previous work that the square root of the variance is the standard deviation, so that should make sense. I'm going to look at all that, and things that might appear on a formula sheet might look like that. Okay, and so just a couple of things to recall, or if you didn't learn them previously, a couple of things to know. The mean is also considered to be what's called the expectation, alright, or expected value, whereas variance is a measure of the spread or the variability. So a couple of things hopefully that add a bit of meaning to this. Now because it's pretty involved, and I want to keep the video sharp to the point, the scope of the video will not cover the derivation or the proofs behind the above formulas for mean, variance, and standard deviation, but I'll just let you know that to find the mean, we do start with our familiar binomial probability calculation formula. Okay, it does start from there, and it's a manipulation of that which would start like this. Okay, and also remember, while we've got it here too, there's just symbols that mu is the mean, or e to the x, e of x, the I should say, is the expected value. So there's your symbols referring to the mean. Okay, and so we would start with our usual distribution and work from there. Likewise for the standard deviation and the variance, that's your variance there. From previous work on discrete probability distributions, we started from there, and the derivation of the formulas comes from that, and that's not what we're going to cover, but that's where it originally comes from. So make sure you do note that the mean, or the expectation, the expected value, all pretty much the same thing, is n times p, so the number of trials multiplied by the probability of success on an individual trial. The variance is that the term above, n times p, which is the same as that n times p, it's multiplied by the complement of p, which some people call q. Okay, so you might see it written as npq sometimes. So n times p times the complement of p. So that's your variance. And of course we know the standard deviation is the square root of the variance, and thus the symbol for standard deviation is that lowercase sigma, which you may have seen before, or sometimes it's written as SD of x, and it's the square root of that variance of x there. Okay, the square root of np times 1 minus p. Okay, so the formula sheet I use had only those on there, so you need to remember the relationship between variance and standard deviation, that square root relationship. Two straightforward and quick examples. Okay, they're both about multiple choice questions. Here's the first example now, and you've got 30 multiple choice questions, each question having 3 possible answers. A student guesses. Now this means a student has no clue, alright, which I know that's a bit hard to believe, but yeah, no clue, no hints, no test wiseness, and none of this canny stuff that some students seem to be able to do. Even if they know only a little bit, they can still sort of manage to get some right by, you know, a bit of reasoning, but we're assuming this student has none of that, so it's purely random. Okay, so let's justify why this is a binomial model Well, it's a random variable, okay, because they're randomly guessing. That's the assumption. And it's right or wrong. So it's success or fail, right or wrong. That's binomial, isn't it? Okay, so she's binomial. So we're defining a success as getting it right, strangely enough, and we have a variable x. Okay, so x is the number of successes. So this all fits that binomial stuff we've been working on. Okay, so number of successes. Okay, so all that's familiar. Now, from here we can see that n equals number of trials is the number of questions, and it's 30 of them. Okay, and we look at if it's purely by guessing on an individual question, the probability of success, little p, is 1 in 3, or a third. Okay, so we have n and we have p. That's good news. Okay, so answering the question quickly now, how many will she expect to get correct? Now that's that expectation, which means we're referring to the mean. Okay, so look out for that keyword, expect. So that's your mean. Alright, even if the question, this question is very kind because it gives you that, but you should be able to function without that given. Alright, so you need to know that. So when you say expect or expectation or expected value or mean, it all means the same thing. So quickly, the calculation is shown there below. That's 30 times a third because it's n times b, and we would expect to get 10 questions right. So 10, that's the number of successes in this scenario. So we would expect to get 10 successes, so 10 questions right. Hey, like, I think you knew that anyway based on a bit of common sense, but you know, the questions do get harder than this, but this just shows that it works as if we model it with a binomial situation. Now 10 questions right, now I don't know too many exams where that's a pass, so that is not good. So we kind of knew that about multiple choice and guessing if you have absolutely no idea. So not good news purely by guessing, but we didn't really expect great news really if the student has no clue. So don't show up to an exam without a clue. There is a bit of free advice from me. And we need to find the variance. Okay, so that's n times p times q, or 1 minus p. You'll probably see it written as such more often. Now we've got n times p above, it's 10. There it is. And the complement of a third is 2/3, so 2/3 of 10 is 20 over 3. 20 over 3. If you wish, you could call it 6 2/3. So that's a measure of the variability. There's a bit of variability there. If we needed to find the standard deviation, we just take the square root of that, probably in that form. Okay, but it hasn't asked us to do that. Okay, the second example and the final one. We have this time 20 multiple choice questions. Each have 5 alternatives, so fewer questions, but we got 5 alternatives for each one. Student has not studied, i.e. they don't know anything, they haven't even got any clues or any way of increasing their chances. Okay, purely random. It's binomial. Okay, it's success or fail. Okay, on each question, right or wrong. Let x be the discrete random variable that describes the number of correct answers. Alright, so we're dealing with x. So we have to do two things with this first part. Determine the expected number of correct answers, that's the mean, and determine the standard deviation of the correct number of questions answered, and take it to 4 decimal places. So let's do that. Alright, so pretty easy. We've got it's 5 alternatives, so it's 1/5 is p. So we've got 20 times a fifth, which is 4. So expect to get 4 right. That's not many. If we expect to get 4 right out of 20, we don't really expect to pass. So for the variance, which is our stepping stone to getting the standard deviation, we have np times the complement of p. Now we've got np up there. There it is. It's 4. So it's 4 times the complement of p. That's 4/5, right? 16 on 5. Optionally, as a decimal, it's 3.2. So the standard deviation is the square root of the variance. which is the square root of 69.5 or the square root of 3.2, and either way, to 4 decimal places, that will come out as 1.7889 according to my calculations. You could write that with surds as an exact value, I guess. Lastly, we've got, they're just trying to make you be a bit more flexible here, a random binomial. We're told it's binomial, random variable z. Just get used to different symbols. We're given the mean. So the mean is 8.4 and the variance is 3.696, and we've got to do something a little bit different here. We've got to determine the probability p and then the number of trials. So this one's a bit juicier. So we're given the mean, and the mean is n times p, so 8.4, this is part 1, 8.4 is n times p. And we don't know n, we don't know p, we've got to find them. What else do we know? Well, we know the variance, and that's 3.696, and the variance is n times p times 1 minus p. And, well, we know that n times p is 8.4, so this bit here is 8.4. So 8.4 times 1 minus p is 3.696. Okay, and we rearrange that and we get 1 minus p is 0.44. So rearranging again, 1 take 0.44 will give us the p we want, and that's 0.56. So this, that first part done. Part 2, you might recall that we had to find n. Alright, now we can use one of these existing formulas, and this one is probably the easiest one. We know what p is, so we're told that 8.4 is n times 0.56. So very simple rearranging and solving. So n is basically a step away, and that's 15 trials. Done and done.